Hello. In this podcast, I will look at three different fields. 1, the gravitational field, 2, the electromagnetic field, and 3, the quantum field. While the first two have strong ontological roots, the third is incoherent. Starting with the gravitational field. Einstein's field theory of gravity was a mathematical model describing a curved space-time fabric distorted by the energy mass of accelerating objects. That is, accelerating in the sense of changing direction, such as in an orbit, not necessarily gathering speed. He did this by arriving at 10 field equations. The geometry of space-time accounted for gravity and solved the conundrum of action at a distance. Einstein said in his autobiographical notes, quote, "The most fascinating subject at the time that I was a student was Maxwell's theory. What made this theory appear revolutionary was the transition from action at a distance to fields as the fundamental variable." Close quote. Einstein wished to unify his equations for the gravitational field with Maxwell's field theory of electromagnetic phenomena encapsulated in Maxwell's equations. At a mathematical level, this would involve deriving each set of equations from something more fundamental. This proved impossible for a number of reasons. Firstly, the ontological belief that the field in both gravity and electromagnetism was separate from the matter it contained, that is, planets or particles. Secondly, the existence of a repulsive charge in the electromagnetic field without a counterpart in the gravitational field. And lastly, the Copenhagen interpretation of quantum mechanics, which reintroduced action at a distance at quantum level. In arriving at his field equations, Einstein relied on 3 principles. The first was the cosmological principle that the universe is homogeneous and isotropic to any observer. This assumption was later supported by the cosmic microwave background that showed an even distribution of mass and energy. A caveat to this is pointed out in a paper by an Italian physicist, Andrea Gomez Valente, and the details are in the book list on my website. The caveat is that we can only observe a fraction of the universe, and if this fraction is indicative of the entire universe, only then will the principle hold. It follows that if our fraction of the universe is special, and I believe it is because it is inhabited by intelligent beings, then this principle is of little use. The second principle is that inertia relates to the distribution of matter, not space. Einstein states, "In a consistent theory of relativity, there can be no inertia relative to space, but only an inertia of masses relative to one another." Close quote. Here Einstein supports Mach and is a departure from Newton's view of an absolute space against which all motion could be measured. The third principle is the equivalence principle, that gravity is equivalent to acceleration. Alternatively, that gravitational mass is equivalent to inertial mass, that is, being in free fall is equivalent to being at rest. Imagine you're looking out of the window of a tall building and someone has fallen off the roof and passes your window. The person accelerating towards the ground at 10 meters per second squared, that is 10 meters per second every second, would experience weightlessness and feel that he was hovering or at rest out with any gravitational field. In a similar way, the person looking out the window, resisting the downward pull of gravity, seems to be physically equivalent to moving upwards out with a gravitational field at an acceleration equal and opposite to that of the person in free fall. In order to balance the effect of gravity, Einstein introduced his cosmological constant, and this would achieve a balanced static universe. When the redshift was discovered by Hubble, and this was interpreted as an expanding universe, Einstein considered his cosmological constant to be his greatest blunder. Notwithstanding that, he did have reservations about the interpretation of the redshift. Quote, "There does arise, however, a strange difficulty. The interpretation of the galactic line shift discovered by Hubble as an expansion, which can hardly be doubted from a theoretical point of view, leads to an origin of this expansion which lies only about 10 to the 9 years ago, while physical astronomy makes it appear that the development of individual stars and systems of stars takes considerably longer. It is in no way known how this incongruity is to be overcome." Close quote. I believe this problem persists despite improved measuring techniques. It should be noted that the accepted version of cosmology, involving the Big Bang, the expanding universe, dark matter and energy, black holes, etc., is being increasingly questioned. It can be argued that the incoherence of the physics is primarily due to adhering to a gravitational model. There is an alternative electric model proposed by the physicist Walter Thornhill, and I have included details of his book and related website in the book list accompanying this podcast. Given that Wikipedia describes it as a pseudoscience, makes one pause and consider if it does pose a threat to the accepted orthodoxy. After all, Alfred North Whitehead constructed his own theory of relativity based on Maxwell's electromagnetism, which for many years had the same predictive power as Einstein's general theory of relativity. Perhaps it needs to be revisited along with some possible solutions from the musings of some 19th century physicist-philosophers. Turning to the electrostatic and quantum fields, as they are both related, but when combined lead to theoretical and mathematical problems. Coulomb arrived at his law, which states that the force between two electric charges is equal to the product of their charges divided by the square of the distance between them, which is the same formula as that used for gravity. And this is measured in amperes per second and is transmuted into a force by applying Coulomb's constant. The same problem of action at a distance crops up as to how each charge influences the other, and the solution was via a field. Dirac's quantum field theory revolved around point particles or charges, that is, a point with no dimensions. When attempting to calculate the electric field around a static point charge using Coulomb's law of electrostatics, together with the equation for the energy density of the electric field, one finds that the point charge is surrounded by an infinite amount of energy. Using Einstein's equation, energy equals mc squared, then it follows that there is an infinite amount of mass. This, of course, was unacceptable. Richard Feynman noted in his lecture on electromagnetic mass, quote, "One large area that we will be concerned with in the future, the interaction of electromagnetic fields with matter, but we want to stop for a moment to show you that this tremendous edifice, which is such a beautiful success in explaining so many phenomena, ultimately falls flat on its face. When you follow any of our physics too far, you find that it always gets into some kind of trouble. Now we want to discuss a serious trouble, the failure of the classical electromagnetic theory." Close quote. I do not believe this is correct. A quantum field theory did not lay a glove on classical electromagnetic theory. Instead, it was the mathematicians of quantum field theory who insisted on characterizing the electron as a point particle with zero dimensions, combined with the misuse of integral calculus that caused the so-called problem. Instead of owning up to this, the dubious ad hoc mathematical procedure of renormalization was relied on to rid the theory of unwanted infinities. There is a note on this procedure in the additional materials section of the website. Historically, Faraday and Maxwell used the concept of a field to explain electromagnetic radiation. The electric and magnetic fields oscillate to produce waves of radiation, but the key difference is that the fields are neutral with balanced charges, not simply one type of subatomic particle with a positive or negative charge. In quantum field theory, the electron is an excitation in an electron field, but it is not clear how a field of negatively charged particles can cohere if they are repelling each other. To sum up, all three fields have anomalies which really need to be removed before any step towards unification takes place. If you want to find out more, please visit my website at quantumid.science, where you will find more in-depth downloadable essays, book lists, additional material, and original papers by some 19th and 20th century physicists. The next podcast is titled The Space Theory of Matter and the Vortex Atom, and I hope you can join me again in tracking down the true identity of the quantum.